and we will begin. Okay, so hopefully without too much dog talking in the background. All right, so we've talked about geometric optics. We've talked about how the eye works, and so now we're going to kind of transition with physical optics into atomic and nuclear physics. So that will give us an idea of what the next step is. Okay. All right. So what happens with waves when they pass through an opening? If the opening is the right size, in other words, if the opening is about the size of the wavelength, then a phenomenon called diffraction will occur. And you have seen this, whether you realize it or not, if you've ever looked at like water waves passing through an opening in like a breakwater, or if you've dropped a stone in some water and it passed through some sort of barrier opening, and you might have seen the waves bend around that opening, and what started out as straight or linear wave fronts then became spherical wave fronts. That phenomenon is called diffraction. Now, for diffraction to occur, the number one most important thing is the opening that they pass through has to be around the same size as the wavelength. And around the same size is like within an order of magnitude or so of the wavelength. So water waves are pretty long wavelength waves, so larger openings work fine. Sound waves have slightly shorter wavelengths. Light waves, visible light especially, has very short wavelengths. So for a water wave, if it were to pass through, say, a doorway opening, for example, it would most likely diffract because it has a long wavelength. A light wave doesn't. A light wave does not diffract around a doorway opening. Sound waves do, because I can be down the hall and I can hear voices coming out of a doorway. Whereas with light passing through that doorway, the edges are sharp. There's not a fuzzy edge where some of the light is bent around the doorway. Okay, so if the opening is large compared to the size of the wavelength, like with light in a doorway, you see sharp edges because it's not going to have a diffraction effect through that doorway. So for light to diffract, it takes a very small opening. Okay. And that last thing is only waves. The only thing that will diffract is things that have wave-like properties. Okay, to be able to diffract, it has to have a wave-like property. So the first example of this is Young's double slit experiment, and it literally is what it sounds like. It's a slit, or it's a mask with two small openings in it. They're separated a distance apart. And when you pass light through it, what happens is each opening now acts like a new light wave source. So this planar wave that comes in here, it's a single wavefront, but when it gets to these two openings, now it becomes two wavefronts because each opening acts like a new source of waves. Then what happens is as these pass outward through the medium, they constructively and destructively interfere, just like we talked about way back in Unit 1. So the light spots in this diagram are where they meet in phase and they constructively interfere. The dark spots in this diagram are where they meet out of phase and they destructively interfere. So what you get is a series of constructive and destructive interference. Now, one thing that I want you to notice is look at exactly halfway in between the two openings. Notice there is bands of constructive interference there. And if I were to put a screen over here, I would see a bright area. I'd see a bright spot. Okay. Now, we don't normally notice this with everyday light because you need to use a coherent light source, meaning that it's all organized in the same phase and they're all polarized in the same direction. We talked a little bit about polarization in the last section. Okay, so Young, when he did his experiment, he even refined it further by only looking at one value of wavelength at a time initially. So he looked at monochromatic light, so only one wavelength that was coherent. And when he passed it through this opening, what he saw was this series of light and dark areas. The brightest of the light areas was actually directly across from the center of the spacing between the two openings. So if light was not a wave, it wouldn't be able to do this, because if it were, it's like trying to walk through a doorway with a 2x4, and if you have it turned the wrong way, you're not going to make it through. Okay, light would not be able to do this if it did not have wave-like properties. So this was empirical evidence that light acted as a wave. Okay, so since these two openings are in phase at the initially, so they both come out of here at the same phase, then you can look at where you're going to have light and dark spots. So since they're initially in phase at each opening, as long as the difference in distance that they travel is a whole wavelength. So if this one's on an up and then this one's on an up and they travel a whole wavelength, they're both going through the same amount of motion, so they'll both still be in phase. Okay, so even if the one, say we're looking at a space over here somewhere, maybe this one travels 5 wavelengths to get there. As long as this one travels a whole number of wavelengths, 6, 7, 8, 9, they'll still both be in phase and they will constructively interfere. But if I look at a spot where one of them has to travel half of a wavelength farther, then one will be on the up and the other one will be down, and they'll destructively interfere. Okay, I think the next picture might show this a little bit, or the picture that's coming up might show this a little bit better. So what he found was what he called fringes. He called it a repeating pattern of light and dark fringes, with the light ones being where the constructive interference was and the dark ones being where the destructive interference was. Let me see if this will pull up here. Okay, can y'all see that okay? I'm assuming you can. All right, so what I've got in this case is I've got sunlight, okay? The red indicates a peak, the yellow indicates a valley. So what we've got here is now these two openings are new sources of waves. Since the center point to this screen is exactly the same distance from each slit, they will constructively interfere at that point and you'll get a bright spot. Then you get bright spots, symmetric bright spots on either side, because this bright spot is exactly one wavelength further away from this right slit than it is the left one. This bright spot is 2 wavelengths further, and so on. So what that means is when they get here, they are constructively interfering. But since this light has to travel further, this bright spot is not as intense because you're losing intensity the further you have to go. So the brightest constructive interference will be the shortest distance the light has to travel, which is directly across from the center, and we call that the central maximum. Okay, so if I were to look at this on a screen, what I would see would be a series of light spots or light lines and dark lines, where this is constructive interference, this is destructive interference, and so on. Okay, so let me get back to my presentation here. Okay, so what he noted was that the sources of waves, or the lights and darks, there was always one directly across from the center, but how the others were spaced was a function of the wavelength that he used. So there was always one, there was always a central maximum directly across from the center of the openings, the center of the slits. But the spacing then, the subsequent spacing was larger or smaller depending on the wavelength of the waves. So we had to look at the path difference, and that's going to be different for different wavelengths. So the wavelength of red light will have a different spacing because it has a different wavelength, because the path length is different. And then to do this mathematically, sometimes we have to use what's called the small angle approximation. You'll see that when we look at an example problem here. Then the further out you go, the less intense the light is, because it has to go further and it spreads out over a larger area and you lose intensity. Just like we lose intensity of sound the further you are away from a source of sound. So here's what this looks like with a little bit of geometry. So I've got my two openings here. They're a distance d apart. There's a screen over here some distance away. My central maximum would be straight across from the center of these two slits. But then this point here is the point of another maximum, say. So I need to figure out how much further this light from slit number 2 has to go. So what I do is I drop a little line down here and I make myself a right triangle. And if I do this, I'm essentially making these two pieces of this triangle the same length. So my path difference is just this little piece right here. Now, if I do a little bit of math using similar triangles, I find out that this angle here, which is the angle of the triangle up to my bright spot, is exactly the same as this angle here for the triangle I drew when I dropped my little thing, perpendicular. So I can write the length of this little piece right here using trig. This is the hypotenuse. This is the angle that I know. So I want the opposite. So it's d sine theta. So my path difference, d sine theta, to get constructive interference has to be a whole number multiple of the wavelength. So the way that I can write that is using the single slit equation. Okay, and the double slit equation. So let's go and look at an example problem of that. So I'm going to stop that.